Hey guys, and welcome back to the fourth and final video in the Learn to Code in C# .NET 5.6 course that I've been producing. If you're just joining at this video, feel free to check out the card right up here that will take you to the entire playlist so that you can start with us from the beginning and learn all of the foundational pieces for how to code. However, if you've been following along this whole time and you're ready to finish out the game and cover our last two topics of collections and error handling, let's get right into it. At the end of the last video, we were trying to add both of our new potions to the player object. Now, as I said in that video, using properties is not the best way to add items to a player because we don't necessarily want to limit the number of items a player can hold, and we don't want to create another property for each new potential item that they might encounter. So that brings us to the topic of grouping related objects or other variables together. In C#, there are two ways to group objects. We can either use arrays or collections. Both arrays and all of the types of collections are reference types and they group data together, but each type of collection and arrays group that data slightly differently. So let's take a minute and discuss some of the intricacies for arrays and some of the collections. Arrays are most useful when working with a fixed number of objects, because once you declare how many values an array can hold, that's it. An array may not change its size to be larger or smaller depending on what the program needs at the time. An array can be set up to hold any type of data, and in our example code, I'll show you how to declare new arrays. There are three different ways to create a new array. The first is to create a new array full of default values. In the first line of our example code, we have int square brackets array1 equals new int square brackets with 5 in it. Let me explain what each part means. The int square brackets array1 declares that the array1 variable will reference an array of int variables, and the square brackets next to int declare that we are creating an array. The new keyword creates a new array, and int5 declares that the new array will hold 5 int values. When you create a new array, you must specify the number of elements the array will hold. However, that number can be derived from a set of values. If we look at line 2, we can see that the line of code does not specify that the array will hold 5 values. Instead, the array derives that it will hold 5 values from the values that are set inside the squiggly braces. Those values can be changed if needed, but since an array cannot adjust its size, array2 will only ever hold 5 values. We can also shorten the array2 syntax by simply assigning the variable to the set of data, like how array3 is assigned as an array. If you don't specify the values being held in the array, the values are set to the default for the type. In this case, the int default is 0, so array1 holds 5 variables that are each set to 0. However, if the array were holding any reference type, like automobiles, that array would hold 5 null values, because the reference types default to null. If you create a new array, chances are that you'll create a single dimensional array, which is an array that only holds values. However, since an array can hold any type of data, what happens if you have an array that holds arrays? An array that holds other arrays is known as a multi-dimensional array. You can add as many dimensions as you'd like, though it's common to stop at a 3-dimensional array. The syntax for declaring a multi-dimensional array is a little different than a single-dimensional array. As you can see here, there's a comma inside the square braces. The comma represents an additional dimension, so 0 commas equals 1 dimension, 1 comma equals 2 dimensions, 2 commas equals 3 dimensions, and so on. So in our 2 example multi-dimensional arrays, we can see that grid is a 2-dimensional array with 2 rows and each row has 5 columns. And grid 3D is a 3-dimensional array with 2 rows and 5 columns and 3 height values in each column. Just like with single-dimensional arrays, you can directly assign the values on creation of the array. So the grid 2D array is holding 2 arrays of 5 values each, just like the original grid array, and we've just assigned the values to it on initialization. So all of that is well and good, but once we create an array, regardless of the number of dimensions, how do we access the values it contains? Well, that's pretty simple. We access the values in the array by specifying the index we want to work with. Arrays hold all of their values at a particular index within them. In C#, array indexes are 0-based, meaning that an array that holds 5 values has a range of indexes from 0 to 4. So if you access any of the index values contained within the array, you'll get the value held at that location. In our example, we have an array that contains 5 integers, and some console.writeLine statements printing the value at a particular index. To get the value at index 0, we write array1 square brackets 0, or read in English as array1 at index 0. That prints out 1 when the statement is executed. Similarly, array1 at index 4 prints out 28. But what would happen if we tried to access array1 at index 5? Well, since arrays are 0-based in C#, index 5 does not exist. If we tried to access an index that doesn't exist within the array, the program will break and we'll get an index out of range exception. So be careful to not access indexes that don't exist. So now that you know the basics of arrays, let's apply what you just learned. Let's go to the player class and create a private array of 10 items that we'll call potions. This is what we'll use to hold the 10 items that the player can use to apply effects to themselves during battle, and then the item will be lost. Then let's add a method called addPotion. We'll use this method to add a new potion to the array at the first empty slot. Create a for loop where the loop variable starts at 0. Then we want the loop to continue while x is less than potions.length. The length property of the array is the number of elements stored in the array. So since an array's indexes go from 0 to length minus 1, we can use x less than potion.length to signify that the for loop should go through each index in the array. Then we can use x++ to finish out the loop. To find the first empty slot, we need to look through each index of the array and check if the spot is null, since the default value of all reference types is null. When we find the null value, we can add the new potion at that index. After you set the index equal to the incoming potion, go ahead and use break to break out of the for loop so that we only set one of the null indexes to that potion. And now that we can add potions, if we simply want to use one, we've got to expose the array. And to do that, let's create an expression body that simply returns the potions array. Now that we have our potions array, we can add the potions to the player. So go back to the guild initiation method in the story service class that we created in the last video and add both potions to the player object. Since we've added potions to the player, we also need to remove the potions when the player uses them. To do that, let's go back to the player class and add in a new remove potions method. To remove the potion from the array, we need to cycle through the array and find the potion that matches and then make that index null. You may remember from a previous video that objects cannot be compared reliably with the double equals. So let's go to the potion class and override the .equals method. Add a new public override equals method to the potion class. When we override the method, the parameter is set as an object. If we try to change that to potion, the method can no longer be overridden. So we have to keep it as object. However, in order to compare two potion objects, they both need to be potion objects. So we need to cast the object to a potion type. While you could use the old casting method of putting the type in parentheses before the value and letting it cast, when working with objects, it's better to use a safer casting method via the is and as keywords. The is keyword performs a cast and returns true if the object is the specified type, so we can check if the object is a potion type object. If it is, then we can cast the object to a potion type without worry. Using the is keyword is a perfectly valid way of doing this, but the SonarLint extension will recommend doing it the second way, as in using an as keyword. The as keyword performs a cast and sets an object equal to the result of that cast. If the cast is successful, the object will be an object of the specified type. And if it's not successful, the new variable will be null. Since the as keyword is the more recommended of the two, go ahead and remove the is implementation and let's implement the as keyword. Here we can see that I set potion equal to object as potion. Then I have to do a null check to ensure that the cast is successful. If potion equals null, then the object is not a potion type and the two are not equal, so we can return false. Else, if potion is not null, we can provide the logic for declaring if the two potion objects are equal, and for that we'll use the potion type and the effect amount. Now our remove potions method in the player class will remove the first potion whose type and the amount are equal to the used object, but there's a few problems with how we've designed this. First, our player is limited to 10 potions since the array's size will never change. Second, when we remove a used potion, all of the other values do not shift down, so we could end up with indexes 0 through 5 being null, and a value at slot 6 in the array, which would look weird when we try to print that out to the player. And finally, because we're using an expression body to expose potions, it's entirely possible that we could just forget to use the add potions and remove potions method. So, while I'm glad we've covered all of this information in order to say that you fully understand arrays and how to work with them, we'll need to solve these issues by switching over to use a collection instead. One of the biggest benefits of using collections is that they will grow and shrink dynamically, which makes them a lot more flexible for working with objects and varying amounts of data as your application's needs change. There are a few different types of collections that we could talk about, but we're only going to talk about two of them in this video: lists and dictionaries. A list is pretty much a dynamic array. That means you can add as many objects to it as you'd like or remove objects from it, and the values will shrink down to fill the newly empty space. Lists have quite a few methods we could talk about, but for our purposes, let's stick to how to create them, add to them, and remove from them. A list is created like all other objects, except that we have to specify a type using angle brackets. So our first list, called names, is an empty list of strings, and it can hold as many string values as we want. Just like with arrays, we can specify some starting values for our list. So names2 has 4 names in it when it's created. However, unlike arrays, the names2 list is not limited to only holding those 4 values. We can add more or remove those values as we want, and the size of list will change as needed. And just like with arrays, you can access a particular value in the array by using the index. Lists are zero-based as well, but instead of a length property, lists use count to signify the number of elements that they contain. Now, if we're trying to loop through every element in a list, and an array for that matter, we can use a special kind of loop known as the for each loop to accomplish that task. The syntax of the for each loop is slightly different than all of the other types of loops. The reason for that is the for each loop is designed to go through every element of an array or collection and perform some action with that element. In our case, the for each loop will go through every element in names and print it out to the console. The way this actually works is that the string name variable is set to the value of each element as the loop iterates over the list, which then allows us to print out the name variable to the console. If we're using custom objects, we can also change individual properties for each element in the list. For example, say I have 3 students in my list all having different grade letters, and I was feeling super generous as a teacher. So in my first for each loop, I could change all of their grade letters to A, and in the second one, we could print them out. Now normally we'd want to do both of these steps in the same for each loop, but I wanted to show you here that the values would actually change. While you can change the value of properties in the list, don't try to change the list itself by adding to it or removing from it while inside of the for each loop. Doing so will break your application. Speaking of adding to and removing from lists, let's talk about how to do that. First, adding is pretty straightforward. You can see I'm adding 3 students to my list right after I create it. Removing it is a bit more complicated, but only a bit. When you call the remove method, you need to provide an object to it. The remove method will remove the first instance of a specific object in the list. In our example, the remove method will remove the object whose ID is 2, even though the name properties have different values. The reason for this is that the equals override method only checks the ID property of students to determine equality. Now that we have a solid grasp on lists, let's go back and update our player class to use lists instead of arrays. So remove the add potion and remove potion methods and change the private backing field and property to use a list of potions instead of an array of potions. Then, back in the guild initiation method, let's change the player.addPotion calls to be player.potions.add. And because we've already overridden the equals method for potions, we'll be able to remove these after the player has used them with no problems. So, we've added the ability for our player to add as many potions as we'd like. However, throughout our game, a player may need to hold more items than just potions. So what we really need to do is create a player inventory dictionary to hold all of the potential items a player may encounter. Before we can do that though, let's talk about dictionaries. A dictionary is a collection of key value pairs. both the key and the value can be any data type. So you could have a dictionary with a string key and a string value, or one with an int key and a string value, or one with an int key and a student object value. So once we create the dictionary though, how do we add a new key value pair to it? Adding a new key value pair is pretty straightforward. You can use the add method for the dictionary to add in a new key value pair. You can see that our parts dictionary has int type keys and string type values. So when we add a new part to the dictionary, we add the key first and then the value. However, when you're adding new pairs to a dictionary, we need to be sure that a pair with that specific key does not exist already. If it does, the application will break because keys must be unique within a dictionary. So we need to use a method called contains_key to check if a key already exists inside the dictionary. If it doesn't, then you can go ahead and add that key. Once you've added some values to the dictionary, you can access them in one of two ways. The first way is through an indexer. Basically the same way you'd access a given index in a list or array, you can access a given value in a dictionary. Except instead of using an actual index, you'll put the key inside the square braces. So when we want to get the value of a certain key in parts, you can see that I can use the one key to get the value of screws. But I can use the key blend for the open with dictionary in the comment there. As an important note, if you try to get the value of a key that doesn't actually exist, the application will break. So be sure to check if the key exists first. Now, if you have a scenario where a key may or may not exist in the dictionary, it's better to use the second method of accessing the value with try_get_value. This method attempts to get the value of the specified key, and if it's successful, the value is assigned to the string value variable. Then try_get_value returns true and allows us to enter the if statement. If the value doesn't exist, the method simply returns false and the application can continue on its way. Now let's put this to work and head back to our application. In our player class, we currently have a list of potions, but we know we're also going to need to hold additional items like the key. So let's create a dictionary called inventory, where each key is an item type and the value is a list of items. Then let's add a new enum to the model's namespace called item type. Inside the item type enum, let's add two values, potion and quest. I'll add some XML documentation to remind me what each type is for, and then now that item type exists, let's make our inventory actually work. To do that, we need to do three things. Update the item base class and the potion class with new properties, update the constructor to initialize the lists in our dictionary, and finally create the methods for adding and removing items from the inventory. First, let's update the item base class with a new property called item type, and set the set accessor to be protected. This way, each item can have its own item type, but the type of the item can only be set in the derived class. After that, go to the potion class and in the potion constructor, set the item type to potion. Now, every new potion item will be created with the potion item type. With that done, we can update our player constructor to hold the inventory. Our player class does not currently have an explicit constructor, so let's add one in using the ctor function. Inside the constructor, let's add two new lists to the inventory dictionary and set the keys as each item type respectively. You can see now that I've got a recommendation to make the inventory object read-only. Read-only means that this value can only be set inside the constructor, and then never changed while that object is in existence. So let's do that to prevent us from accidentally setting inventory to something else elsewhere inside the class. Finally, we need to create an add, remove, and get items method to fully utilize our inventory. Let's start with the add item method, which will be a public void method that has an item parameter. Inside that method, all we need to do is get the list for that particular item's type and add the item to that list. Now, this won't always be the best way to do this, but since we know that the dictionary will always have a list for each item type because we set that up in the constructor, it works perfectly. The remove item method is also going to be a public void method that has an item parameter, and the inside will also have a single line of code, but instead of adding the item, let's remove the item. The final method we're creating is going to return a list of items, and we'll call it getAllItemsInInventory. It will also have an item type parameter. Now, the point of this method is to specify the type of the item and get all of the items in our inventory that meet that item type. So inside the method, we can write return inventory type to return a list of all of the items of that type. And just like that, our inventory is complete, so we can remove our previous potions list. Now that we've reworked our inventory, let's head back to the story service and add in the potions. Simply change the code to player.addItem and you're all good to go. And now we can move on with the game. So let's go back to the program class and give them some more content. At this point, we need the player to choose either to take the test or to leave the guild forever. So let's get that done. We'll start with the leaving of the guild. Let's create a new method in the story service class called initiation decision to handle this first choice. This method will help the player decide if they want to take the test or leave the guild hall forever, and it will return a bool value after that player has decided. We'll return true if the player wants to take the test and false if they don't. Now we need to print the options that the player has to the console. However, I don't want to constantly have to type out a new menu each time, so let's make a new class called menu service to handle getting the player's choice. Inside the menu service, add a method called getPlayerChoice that takes in a string array of options. This way we can print out all of the menu options in a standard format and get the player's input back in one location. So add in a for loop that accesses each index in the array and prints it out. Then we want to get the choice back from the user, which I'll put in another method so that we can reuse that code later when we need it. And finally, we want to verify that the user's choice is among the possible values given in our menu. But what if the player's choice isn't a number? What if they accidentally type a letter or some non-numeric character? If they do that, we'll get an exception. And that leads us to our final in-depth topic of error handling. There are three types of errors when you're coding: logical errors, compile time errors, and runtime errors. Compile time errors are the easiest to handle because these errors prevent your application from building and running, and Visual Studio handles a vast majority of these errors for you by letting you know that they exist in the error list window in Visual Studio. Logical errors are the most common error though, because this error is an issue with the outcome of a piece of code. For example, if you add 2 plus 2, you would expect 4 as the result. A logical error would have occurred if you got any other number than 4. Now, these errors are also some of the hardest errors to fix because you have to locate where you wrote bad code into your application. And finally, we have runtime errors. These types of errors have the potential to break your application and crash the program. Runtime errors are broken down into two categories: actual fatal errors and exceptions. There's nothing really you can do about an actual fatal error, so we're not really going to focus on those, and those are extremely rare. Instead, let's talk about exceptions and how to handle them. Exceptions occur when something unexpected, something impossible, or something that isn't allowed by the C# language occurs in the code. For example, if the user typed a letter when entering their menu option choice, then we'll get an exception when the code tries to convert that letter to an integer. Exceptions use a throw and catch terminology when being worked with, so when trying to convert a letter to an int value causes a format exception, that format exception will be thrown by the application. In order for the application to not crash as a result of the thrown exception, we must catch the exception and handle it in our code. If we don't catch the exception in some way, the application will crash. So, how do we catch exceptions? Well, we can use something called a try-catch block to attempt potentially risky lines of code and catch any exceptions that are thrown from those lines of code. Let me show you how this works by adding a try-catch block in the getPlayerChoice method. Inside the do-while loop and above the for loop, let's add in the try block. Then move all of the contents of our do-while loop into the try block. This will then tell the application to attempt to execute this code as normal. Now, after the try block, we need to add a catch block. The catch block requires that we specify which exception we're trying to catch. So we can specify a format exception in the parentheses for this catch block. If a format exception occurs in the try block, we know that something wasn't entered correctly. So we can reset the choice to -1, clear the console, and then tell the user to input only the number of their choice inside our catch block. This allows us to account for and properly handle any format exceptions that can possibly occur while the user is working with our code. However, there are other exceptions that might occur if we've coded something poorly here. So let's add another catch block to account for those. Let's add another catch block to handle any other exception. This way, if something else goes wrong during the menu execution, we can safely handle it and the application can keep going. You'll have noticed that the second catch block actually creates a variable called EX when it's triggered. This exception variable will have information about what occurred that will help you troubleshoot any issues that arise during execution. Now, if you don't care about the error message or stack trace or any of that other data, you don't have to create the variable like our first catch block doesn't create the variable. But if you want the information, you will need that variable. Now, you should know that the first catch block that executes will be the only one that executes. If we get a format exception, then only the format exception catch block will trigger. However, if we get any other exception other than a format exception, the exception block will trigger. Because of this, you want to handle exceptions as specifically as possible. Since exception is the base class of all other exceptions, it is the widest net you can cast to catch exceptions. So always list your catch blocks from smallest and most specific possible exception to largest and most general possible exceptions. At this point, you should have a solid understanding of all of the foundational pieces you need to create just about any application. So the only thing left for us to do is finish out our game, which will end when the user finds the key in the dungeon. Let's head back to the initiation decision method, and let's use what we've created to get the choice back from our user. So add in a new string array to the method with two menu options, take the test and leave the guild. Then pass that array into the getPlayerChoice method and store the result. Finally, we're returning a bool value, so we can return the result of a Boolean expression. And since arrays are zero-based, let's return whether or not they chose to take the test by using choice equals 0. So back in the main method, let's use the method that we just created. Add in an if-else statement that evaluates if the user wants to take the test. If they don't want to, let's have them leave the guild forever and end the game. But if they do want to take the test, let's have them take the test. Now you can add your own story printouts to the code in these methods, so I won't waste your time showing these off. Once you code the story scenes for leaving and taking the test, let's have the player explore the guild's dungeon. Now we're only going to explore the guild's dungeon in this game, but if you were to try and fully flesh out the game after the player has passed the initial guild test, you would want a guild service class to hold all of that code. So let's go ahead and do that and set you up to continue this on your own. Add in a new class called Dungeon Service and create a method called Explore Guild Dungeon that takes in a player parameter. Then call that method from the main method so that the player moves into the dungeon code after they decide to take the test. In order to have the player move around a dungeon, we need to actually create a dungeon. And to keep things simple, let's use a 2D array to hold our map layout. Now you could use a 2D int array to mark up the map and signify what spaces are okay, but again, ints have no inherent meaning. So let's make a dungeon space enum so that we can more easily declare what space is what. Add an enum called dungeon space to your models folder, and then we'll add the following values to it: empty, treasure, special feature, entrance, and wall. Now you can add more if you want to and take the game further than I will, but this will be enough for me for now. So let's add a 2D array of dungeon space values with 3 rows and 3 columns called map to our method. Now let's fill in the map with some values. You can fill yours in however you want, but I'm going to fill mine in like this. The top row will have 2 empty spaces, and the treasure spot will be in the middle top space. The middle row will have a special feature in the leftmost room and 2 walls to prevent the character from moving through the middle, and middle right spaces. And then our bottom row will be empty except for the entrance, which will appear in the bottom middle row. Now for this part of the game, the player is trapped in this map until they find the key. So we need to add a bool variable to act as a flag for whether or not the player has found the key. Then let's remind the player what their objective is and trap them in a do-while loop that won't end until they find that key. Next, we need to provide them with their dungeon location so that they can know which way they can move. But more importantly, we need to store where that player currently is in the dungeon so that they can't walk through walls or leave our map accidentally. Let's create a new class for storing the location and call it location. The location class needs 2 int properties called row and column, And let's be sure to add a non-default constructor that forces us to set the row and column at the creation of our location object. Then we can set the location of the player to the spot we designated at the entrance, which is 2, 1. Remember that 2D arrays are 0-based, so our code in the upper left-hand corner of the map is 0, 0, and the bottom right-hand corner of the map is 2, 2. Now inside the do-while loop, let's tell the player what their current position is and ask them what they'd like to do. Now we need to make a decision about what we're going to allow the player to do and present those options using the menu service. So I think I'll limit the player to be able to move around the dungeon and investigate their current space. So let's create a class level array called dungeon actions that contain those two options. When we present the player with these two options, we need to get back their response and have them move or investigate that space. But since the getPlayerChoice method in the menu service returns an ints, and ints have no inherent value, let's make another enum for what action the player has chosen and cast their choice to that value. So add in an enum called dungeon actions, and let's make the values move and investigate. Then we can take the choice from the menu service and cast it to a dungeon actions value. And then we can switch on that value and create cases for move and investigate. Inside the case for moving around, we can ask them which direction they'd like to move. Now in the 2D space, there's really only 4 directions: forward, backward, left, and right. So just like the dungeon actions, let's create an array of navigational choices and have the player select which way they would like to move. But once they've selected how they want to move, how do we actually move the player into a new space? Well, for this, we'll need to make a new service and write some code to ensure that the player can move around on the map appropriately. Create a new service class called Navigation Service. This class will contain a single method called movePlayerLocation. We'll need this method to take in a location parameter, the direction the player wants to move, and the map the player is moving on in order for the method to determine if a player can move to that requested location and then move that player to that location. But before we can start working on the logic for this method, let's add in some class level constants to ensure that navigation is done correctly. To start, we'll create 2 constants for max forward and max left. Both of these should be set to 0, because the upper bounds of a 2D array will always be 0, and the left bound for a 2D array is always 0. Then we'll add in a constant value for moving in each of the possible 4 directions. Move left and move forward should be set to -1, because as the player moves left or forward on our map, the row or column will decrease by 1. Move right and move backwards should be set to +1, because as the player moves right and backwards on the map, the row or column will increase by 1. And with that in place, we can now add in the movement logic to move player location. Before we can move the player, we need to know a few things, like what location the player is currently in, which is handled by our location object. We also need to know the direction that the player wants to move, which comes in on our string movement direction variable. But that really isn't workable in its current form for reasons we'll get into later. And we need to know what the maximum bounds of our 2D map are. So let's get all of those values. To start with, we need the direction the player wants to move. We currently have this as a string, but any related group of values should be set in an enum if we're going to follow best coding practices. Then let's create an enum called navigation that contains the directions that can be moved in: forward, backward, left, and right. Now that we have that, let's parse the string into an enum. Parsing an enum is pretty straightforward. You just need to use enum.parse and cast the final result to the expected enum. So enum.parse, type of navigation, and then movement direction does this for us. The code parses the string contained inside movement direction into the enum type navigation. So if the string matches any of the values contained inside the enum, enum.parse will return an object whose value is the equivalent of that enum's value. Then we need to cast that object to be the desired enum, and we're done. This gives us a more maintainable value for working with the direction that the player wants to move. That said, now let's go back and fix the navigation array in the dungeon service to use the enumerated values instead of the pure strings. This will prevent any problems if we happen to rename the enum value at any point in our future. Next, we can grab the map's dimension by using a method that arrays have called getLength. In the getLength method, we can pass in the dimension we're looking for and find out how many elements are stored at that level. So getLength 0 tells us we have 3 elements in the first dimension of our array. Since arrays are 0 based though, we need to subtract 1 from that answer to get the max down index. Then getLength 1 tells us that each of our second dimension arrays have 3 elements in them, and we could subtract 1 again to get the maximum right index. Now that we have all of the required information, let's make the player move left. So create a switch based on the direction, and let's start with case navigation.left. We need to determine if the player can move left, and if so, move them left. If not, we can just say that the player cannot move left. So how would we determine if the player can move left? Well, the player cannot move left in these 2 scenarios. First, they cannot move left if the player's location column equals the max left value, because they're already as left as they can possibly be on the map. The second scenario is we don't want them to be able to move into spaces that are marked as a wall. So if the player location column is greater than max left, and the space they're trying to move into is not a wall space, let's let them move left by adding the move left constant to their column value. Moving right is pretty much the exact same thing as moving left. If the player's column location is less than the maximum right index and they aren't trying to move into a wall space, then they're good and they can move. Finally, moving forward and backward is very similar to moving left and right, but instead of checking the column value of our location object, we need to check the row value. With all of the directions and moving logic in place, we can finish out this option by calling the movePlayerLocation method and passing in all of the required values. Then add a break and the players can now move around the map. The second action the player can take is investigating their current space. So we need to come up with some responses for what they'll see in their current location if they choose to investigate. To start this process, we need to get the space the player is currently located in. So create a method called getDungeonSpace that takes in the map and the current location and returns a dungeon space enum value. Inside the method, we just need to return the map's value at the current location. Once we have the space, we need to create some messages for what the player might find in this space. Let's create a method called getInvestigationResults and pass in the dungeon space and a string value for whatever special feature here exists. Now you can add in your own messages, but for my game, the player won't find anything interesting in an empty space. I'll also tell the player about the dungeon entrance if they happen to be in that space, and I'll notify them about whatever special feature exists if they're in that space, and that a chest is in their current location if they're in the treasure space. We'll add a default here just in case we add any new potential spaces in the future, and then we can print all of those responses out to the console, and we're done. Finally, if the player investigates the space and finds the treasure, we need to ask them if they want to open it. So if the space contains treasure, let's offer them an option to open the chest. However, this is a single option, so instead of using our original menu service method, we'll need to create a new method just to get confirmation of their choice. The getConfirmation method should return a bool value, and it should take in the confirmation text that we need to provide. Just like with the getPlayerChoice method, we want to re-offer our players the options if they mess up their choice. So let's throw this in a do-while loop and then add a try-catch to ensure the application doesn't break if the user messes something up. Then, since this method is always going to be a yes or no, we can simply return whether or not the user's choice corresponds to the yes option. If we get a positive confirmation that the player wants to open the chest, all we need to do is set the key found flag to true and print a message telling the user what they found. Because this ends our do-while loop, let's add a final message letting the user know that they just teleported back to the guild hall. And since this is the last piece of code in our game, the game will end after the player finds the key. Alright y'all, you have completed the Learn to Program in .NET 5.6 C# course, and you've built the vast majority of a text-based RPG game in C#. So give yourself a pat on the back, you've really earned it, especially if you understand and have digested all of the information that we've put out in this course. Now, if you wanted to expand your game and add in fighting for using the stats that we added for the player and add in more items for the inventory and how to use those and everything, you now have all of the skills to be able to do that. but since this course was really to teach you how to program and not just to build the game, I'm going to go ahead and consider us done. If you enjoyed the course, smash the like button, and if you want to see more courses like this for different programming topics or more game dev in general type stuff, consider subscribing. Otherwise, guys, I'm Sir Pinkbeard. Thanks for watching, and I will see you guys in the next one.